Hello everyone, welcome to lecture 4. This is the first part of lecture 4, so we're going to talk about the how to solve different functions, which includes the linear functions or linear equations, the quadratic equations, exponential equations, and logarithmic equations. We also talk about the sign charts methods, which is used to help us solve the inequality equations. Okay, so let's get started. Now, the first example, which is very simple, right? So we just solve this linear equation. We can move the 3x to the left side. So 6x minus 3x equals to 1 minus 2. It's just a simple manipulation. 3x equals to minus 1. So this gives us x equals to minus 1 over 3, right? So that's a easy case. Now let's look at the quadratic equation. So when we talk about the quadratic equation, we need to know that this actually follows a general form of a quadratic equation, which is a x squared plus bx plus 3 equals to 0. So this is a general sort of form of a particular quadratic equation, and the condition is that a cannot be 0. So this is our sort of leading coefficients we talked about earlier. So this is a polynomial function, and this is the so-called also the standard form. And also we have a, b, c as our constants. Right, they do not change, and what's changing is only the x itself. So if x squared, we'll have x. Now the question is, how do we get the solution for x? So following this particular standard form, there's a sort of closed form solution for this particular form, which is that x will be equal to, right? So the denominator would be 2 times a. So the numerator would be minus b plus and minus, right? The square root of another expression, which is b squared minus 4 times a and c. Right. So this portion is called the discriminant, and it's called discriminant. This is an important component is because it determines sort of how many solutions we have. So if the determinant is positive, right, then we have 2 solutions or 2 real numbers in terms of x, so 2 solutions. So if it is equal to 0, then this term cancels out. Then we only have 1 solution, right? So which is very intuitive. You just b minus b over 2a, right? So if it is negative, then because this term actually cannot be negative, then this would lead to us to no solution. So there will be no solution in this case. So basically, this gives us a tool to detect how many solutions we would have for this particular quadratic equation. Right. So now let's plug in back to the expression we have earlier. Now, so look at this expression. We can just plug in the formula and carry on with the calculation. So we know that the discriminants would be actually above 0, and then we can calculate. In this case, there are 2 solutions. So we can just plug in the numbers. So 2 times -5, and then plug in the b components. So 75.1 minus plus the discriminant here, which is 0.1 square minus 4 times -5 times -156. So this example is actually a simple example, but just choosing so that the calculation is actually very simple. You can just plug in the formula once we detect this expression, this term is actually positive. So the rest of the analysis just carries forward. So you can just plug in and then calculate what's the value for x. Right, so in this case, when you are calculating, when at this step, you can just carry on and use the calculator to calculate the results for x. All right, now let's move on. So let's look at how to solve exponential equation. So the exponential equation would be something like this. So 2 to the power of x, this will give us x equals to 3, right? Which is very intuitive. This was something we covered in the last lecture as well. So for solving this expression here, so a0 is actually a constant. So in this case, we can just cancel it out. So no constant, and we have 1 over 2 equals to 2 e to the power of, this is a very small term, right, times t. So in this case, we can apply apply the logarithmic transformation to both sides, so that we have ln 1 over 2. So in this case, I'm taking the natural logarithm of both sides, so that this one goes away to the base of e. So we have this particular term here. And now we can continue with the rest. So move this portion here and then get the value of t. So usually at this step, it's not necessary to calculate the exact value of t. You can just say t will be equal to ln 1 over 2 minus 0.0001224. So that will be good enough. All right. So now let's look at how to solve a logarithmic equation. So we already looked at a few examples on how to solve this. So in this case, it's very intuitive. We can just carry forward by transforming the expression to x equals to 2 to the power of 3, which is 8 in this case, right? However, there's one point I want to mention here, which is that the particular x should be, there's a condition, which is that it should be positive, right? It cannot be 0, it cannot be negative. So always remember that we're looking at a graph of the logarithmic function where it's either this or this, and the domain of x is always positive for logarithmic functions, right? So that's just something to keep in mind. Okay, so now let's look at the sign chart method. This is actually comes to play when we are solving an inequality function. For example, x plus 1 divided by x minus 2 bigger than 1. Now, without the sign chart methods, we can typically solve the function like this. So we have two components, x plus 1 and x minus 2. So we're asking it to be, the results to be positive, right? So so this means that either, so there are two conditions, either both are positive, right? Or second condition, both are negative. So there are two cases. So for the both means like this is and sign. So this gives us the result, which is that x bigger than -1 and x bigger than 2. And then this means that x should be bigger than 2 because we are taking the AND condition. So both should apply. In this case, we go with a strict condition. So similarly, x less than -1 and less than 2. So this gives us the results. X should be less than or equal less than -1, right? So this is how we can get the result without having to use the sign chart method, right? However, one thing to keep in mind is that okay, let me just re-express. So we can say, so we can write the result as x as -1 or less bigger than 2, right? So this is just one way. Another way is to write this is that x belongs to the domain, which is -infinity, -1, union 2 to the +infinity. So this is another way to express the same results. So this is a union number. This is the different ranges we have. Right. So the sign chart methods is actually essentially give us the handle to look at what is the sign of the function at different sort of intervals. So now, first question is, what is an interval, right? So interval, or the interval is defined actually by a partition number. So we need to know what is a partition number. So a partition number is a number which makes the function itself, right? So the function itself f, equals to 0, f equals to 0, or it's discontinuous. Discontinuous. So so if we have a point that's the value of x is equal to 0 or is continuous at discontinuous at this particular point, then we call it as a partition number. So usually the way how we find the partition number is two cases. One, if it's equal to 0, right? So come to this particular expression here, what makes the expression equal to 0? Of course, x equals to -1. And what makes it discontinuous? Of course, x is equal to 2 because x cannot be 2 at this particular point. So that's the point where the function is discontinuous, right? So we have these 2 points. Now, if we draw a line here, so a sign chart essentially refers to a line, right? It's a real line, right? So this is infinity, negative infinity. We have these 2 points, -1 and 2 here. Right? So these are 2 points. So the sign chart essentially refers to the situations that when f itself, right? So when f is continuous within a range a and b, right? So if it's within a range a and b, and also f is not equal to 0, right? So it's continuous within this range, and also it's not equal to 0, then we see that f of x is either above 0 uniformly everywhere, or f of x is below 0. So basically, it has takes on the uniform sign within the whole range. So let's draw some graphs. So for example, if you look at any other graph, if it's the satisfied condition, right, within this range a and b, it's continuous. That is continuous, right? And also it's not equal to 0. So it's always above 0 in this range. Then f itself is always above 0 in this case. There are, however, 2 different cases. So situation 1, if f is not continuous, right? So, or say you can say it's discontinuous, continuous. So what happens now? F could be something like this. So we have this chart here. So this could be the example of f. So f is not continuous at this specific point. Now, if we are looking at a range a to b, right, then f it can change in terms of the sign. So it's not uniformly above or below 0. So that's one situation, right? So that's violates our condition here. Now, second case is what if f can be 0, right? This is a second condition. Now, if f can be 0, then I can draw something like this, right? So just any graph here. This is A, this is again B. So if x can be 0, if f of x can be 0 within this range, then we can actually cross these points, and this makes the sign also changes. So in this case, both cases. So this is the case where the sign changes. There's another case where the sign changes. So that's cannot lead to the conclusion we have. So in this case, basically the takeaway is that if f is continuous, right, within the range, and also is not equal to 0 anywhere within this range, then we can say f is uniformly above 0 or below 0, right? So let's use this rule. Look at this expression here. So identify the partition numbers. We know that these 3 regions, region 1, region 2, region 3. Right? So this is region 1, region 2, region 3. So these regions are gonna be taking a uniform sign. Either they are positive or negative, right? Because they satisfy these 2 conditions, which is that continuous within the respective range, and also is not equal to 0. This is what we know. So I have another thing which is called test number. So we know that they are actually taking a uniform sign. We just don't know whether it's positive or negative. So let's just take some random numbers. See if I take -2, right? And then this portion is actually the result will be, let's do a calculation. -2 plus 1, -2 minus 2, it could be positive, bigger than 0, right? So in this case, this range should be positive. And then say we take a number 0. These are just some random test numbers, and the result is 1/2 negative, right? So it's negative. So the third case can say number 5. Of course, 5 is 6/4 is also positive. So this makes it positive, right? So we are essentially constructing a line sign chart such that we have configured the direction or the sign of the function across different intervals, and these intervals are partitioned by this so-called partition number, right? So we first find the partition number. Well, it is either the value is 0, right? The value of function, or it is continuous or it's discontinuous. So these are how the partition numbers are determined. So this first step. The second step would be to find the test numbers, like the -2. You can choose any number you want, and then this is to identify the sign of the respective regions, respective intervals. And then with this, we know that these are the solutions we're asking for, right? So these two ranges, which correspond to the solutions we derived earlier, right? So that's just some introduction on the sign chart method, and this method actually will be used later on in our other topics. And yeah, I think that's it for this lecture, and hope to see you in part 2 of the same lecture. Thank you.